Hello everyone, my name is Jesús Alejandro Arias Hernández. I'm a student of mechanical engineering in the Instituto Tecnológico de Morelia, and in this occasion I'm going to talk to you about the project I'm currently working in, porous silicon carbide manufacturing. In this work, we study porous silicon carbide manufacture using Luffa as an organic pore former and glass particles as bonding agents. Also, we use two different compositions with different silicon carbide particle sizes in order to see how this variable affects the porosity in the material. The main objective in this work is for sure produce and characterize porous silicon carbide ceramics. Also, perform capillarity tests on the finished samples. What makes porous silicon carbide ceramics so attractive? Well, the porous structure endows the materials with properties that we cannot find in a completely dense material. Properties such as a great permeability, a great superficial area, and a very low density. By the other hand, silicon carbide is an advanced engineering ceramic with high resistance to harsh environments, high thermal conductivity, usually compared with copper, and it is an electrical semiconductor. The combination of these properties makes silicon carbide materials very useful in many applications, some of them in hydrogen production plants, catalyzers, or even supercapacitors. In order to produce the samples, we firstly mix all the components with water in a magnetic stirrer. After that, we dry the powders in a convection oven. And by last, we thermally treat the samples in a sintering oven at a temperature of 775 Celsius degrees, with different holding times. The capillary tests were performed with water as liquid medium. As we can see in the SEM images, both silicon carbide types shows the same angular grain morphology. However, the average particle size is very different between them. In the first type, we can find that the average particle size is 21.56 micrometers, while in the second type, the average particle size is 76.74 micrometers. Before talking about the holding time effect on the materials, we can actually notice the effect of the particle size on them. We can see that in every case, the first type of silicon carbide powder reached a higher porosity in comparison with the second type. However, holding time not only affected the porosity in the materials, it also affected the material stiffness. We can see in the samples treated with just 50 minutes of holding time shows very little stiffness in comparison with the rest of the samples. The same images of both samples reveals various things. The first one is the lack of Luffa presence, meaning its complete elimination during the thermal treatment. We can also notice the complex and very irregular porosity on both samples, probably caused by the Luffa elimination or the interstices between silicon carbide particles. This images also shows the way the glass bonds silicon carbide particles together. The electron through microanalysis reveals the composition of the bridges between silicon carbide particles. This composition corresponds to the oxides in the glass used as an additive in this work. As the porosity in the sample was very complex and irregular, the Lucas-Washburn law was used to determine the pore radius of each sample. The samples produced with the first type of silicon carbide powder have a pore radius between 2 and 3 micrometers, while on the other hand, the samples produced with the second type of silicon carbide powders have a pore radius up to 7 micrometers. In conclusion, porous silicon carbide ceramics can be produced using both types of silicon carbide powders, Luffa and glass, at temperatures as low as 775 Celsius degrees. These works also show that the properties of these materials were highly affected by the particle size of the silicon carbide. Thank you for your attention.